Okay, this is quiz 9, and problem 1. You had refrigerant 134 going through a valve, and it came in at 3 kilograms per second and 30 degrees as a liquid. So as a liquid, its properties were, if we take those to be approximately the same as the saturated liquid properties, then that would be, let's see, H1 would be equal to 93.58, and S1, we're going to need that later, would be equal to 0.34789. So coming out of the valve, we were told it was 10 degrees C, and H2 would be equal to H1, which is 93.58. Well, we know that if we go to low enough pressure, we'll flash, and that causes the temperature to drop when a liquid passes through a valve. If it gets below its vapor pressure, then it will start to evaporate, and the energy to evaporate causes the overall temperature to drop. So since the temperature's dropped, we know that some must have evaporated. So that would be H2 is 1 minus X HF, and HF was 65.43 plus X times Hg, and Hg was 256.16. Solving for X coming out of the valve, we have X equals 0.1476, or 14.76% vapor coming out of the valve. So now you can calculate S2 is equal to 1 minus X SF, and SF at 10 degrees is 0.25286, and X times Sg, and Sg is 0.92461, and plugging in the X from above, we get this is 0.3520, and that's kilojoules per kilogram K. So S generated is equal to S out minus S in, or 0.3520 minus 0.34789, or 0.00411. So S generated. Irreversibility, defined as S generated times the temperature of the surroundings, which was given to you as 30 degrees. So that's 30 plus 273 would be 303 Kelvin, times the S generated per mass, 0.00411, times the mass flow, 3, and that comes out to 3.74 kilowatts per Kelvin. So that took care of problem 1. Problem 2, we have steam going through a turbine. The turbine is insulated, and we'll treat it as an adiabatic turbine. So the energy that comes in has to go out. If we assume steady state, N equals out, we have W dot here. The entropy balance on the turbine, if it were adiabatic and reversible, S2 would be equal to S1. Let's call that S2 ideal equals S1. Let's see, before we do that though, let's look at the state going in. Going into the turbine, you have H1 is at 100 psi and 1000 degrees Fahrenheit. H equals 1532.4. Can look that up from the table pretty easily. H out of the turbine was given as, let's call it H1. The H2 was a function of, let's see, it was told to come out of the turbine at 200 degrees Fahrenheit and 1 psi, from which you find the H2 is, and you can look that up directly from the tables, H2 is 1150.1. So the work that you got out of the turbine, and that's the real work because we measured the temperature coming out, the real work per mass is equal to 1532, get this from your energy balance, minus 1150, 32.2, let's say. It's 1150.1 equals 382.3. Let's see. Oops, sorry, that's 1532.4 actually. So that's 382.3. That would be BTUs per pound of steam that goes through the turbine. Now, if we use this fact up here, S2 equals S1 for the ideal case, then we have, what I do is follow it on the Moliere chart. Go into the turbine. Your Moliere chart looks something like this. This is S down here, and this is H here. Coming in, temperature is 1,000. Pressure lines, let me draw those in red. Here's your pressure line at, what was it, 100 psi. Then we have another pressure line here at 1 psi. And so what I would do, and let me draw this in green to indicate the ideal path through the turbine would be at constant entropy. So you drop along into, it gets you just inside the saturated region. If you do this with the tables, you have to calculate quality, and it's a little more time consuming, but if we use the Moliere chart, it gets me just inside the saturated region. And I read off this ideal enthalpy here, H2 ideal, let's call it, was 462.4 approximately. So if we actually, I think I did this with the tables, but you could get very close using Moliere chart. 1532.4. Oh no, I'm sorry. Whoa. H2 did do this with the Moliere chart. H2 was 1070. Got a little ahead of myself. I was looking at that number and thought, how did I get so precise? You can only get so precise with the Moliere chart reading it. If you use the straight edge, you can improve that a little bit. So I came up with 1070, and the work ideal is H2 minus H1, sorry, H1 minus H2 ideal, or 1574, 1532 minus 1070. That's the number I had before, 462.4. There's your work that you'd ideally get from that turbine. So let me go over it again. Came into the turbine at state 1, dropped at a constant entropy through the turbine until I got to my outlet pressure, read the enthalpy, and it was approximately 1070. So the energy balance gives you 1532.4 minus 1070, and the work ideal is 462.4. Not surprising that we got less work from that, 382.3 from the real turbine. So the efficiency is simply the ideal work, 382.3 divided by 462.4, and that comes out to 0.83, or an efficiency compared to isentropic operation, your efficiency was 83%. Okay. One last thing, going through that real turbine, you wind up with less work drawn out. Here's the ideal work. The real work is 83% of that, so you drop to a lower level. You could recalculate that enthalpy coming out, and that would be to the right, but you'd still be on this 1 psi line, so you'd be up a little on enthalpy and to the right on entropy. So you always wind up in an adiabatic turbine with entropy increasing just a tad there. So that takes care of quiz 9. Turbines and, let's see, adiabatic efficiency and irreversibility.